Welcome to A-level chemistry lessons. In this video, we are looking at how to calculate lattice energy using the Born-Haber cycle. The Born-Haber cycle can be reduced to a single equation. The single equation is as follows. Heat of formation is equals to heat of atomization plus dissociation energy plus sum of ionization energy plus sum of electron affinities plus lattice energy. Note, in this general equation, the electron affinity is added. However, when plugging in a value, determine whether the energy is released or absorbed for each electron affinity. If energy is released, put a negative sign in front of the value. If energy is absorbed, the value should be positive. Now, that doesn't make sense, I know. But let's look at the actual calculations and you'll see that it's actually making sense. So, rearrangement to solve for lattice energy gives the equation. Lattice energy is equals to this one. Now, for me, I would advise you learned about a substitution method. So you can memorize one formula and then you just be substituting instead of making whatever the subject of the formula, wasting time. So just substitution method is going to be faster in all our calculations. All right, let's look at the example that we have here. So it says, given the following information, calculate the lattice enthalpy of sodium chloride lattice. So this is the information that we've been given here. Okay, this is the information that we've been given here. And then the question is, we are calculating the lattice enthalpy. In other words, enthalpy is simply energy. So we're just trying to calculate the lattice energy. Now, if you remember the formula that we had, we were saying enthalpy change of formation, okay? Enthalpy change, so delta H of formation is equals to, then you add all the atomization energy, so you add the atomization energy, you add the dissociation energy, the ionization energy, and the lattice energy. So what is going to happen here is, let me just remove this part here. So what is going to be happening here is, you write the general formula. So here is your solution. So you can see that enthalpy change of formation will be given by enthalpy change of atomization of sodium, enthalpy change of the first ionization energy of sodium, and then you also have the bond dissociation of chlorine, then you have the first electron affinity of chlorine, and then that's when you have the lattice energy. Now, the secret here, ladies and gentlemen, is where you are starting from. They've told you that it's sodium chloride. So you know that sodium chloride is a product of this plus Cl2. Now, remember what I said. This part, you know that when it is ionized, ionization is the final step for the metal side. So when this one is ionized, it is going to end up as Na plus. So you know that it only needs 1. So if it's plus on the other side, then it will also need Cl minus when it comes to adding these two to form an ionic lattice. So if you have this at the back of your mind, then it will not be a problem that you are going to need the half Cl2, because this also might be important in the calculation. So you should bear in mind whether you are putting a half here or not. All right, let's move on. So having understood this aspect here, let's continue and also just know that since this is a sodium, it is a solid as it starts. The next thing is it will go to a gas and then it will be ionized. So we need atomization of sodium. We need atomization of sodium. Okay. So the atomization of sodium, which is the one we've been given here, and then do we have first ionization of sodium? Yes, we have this one. And then bond dissociation of Cl2, which is the bond dissociation of Cl2. Now, because here, this value is the bond dissociation of Cl2, and what we have in the final equation is just 1 Cl, it means that this value, we need to divide it by 2 as we substitute it into the equation. Then electron affinity. So this one, when it is dissociated, it is giving us Cl, 1 Cl as a gas. But when you add 1 electron, it will eventually give us this one. So since it has a variance of 1, meaning it only has first electron affinity. So the electron affinity is as given here. And then the enthalpy change of formation is as given here. So you substitute these values into the equation. This is what you're going to come up with. So you come up with this value. You can pause the video, try to go through the calculation, provided you have you are not mathematically sick. I expect that you are not mathematically sick anyway, because you are doing A-level chemistry. Let's look at a sample exam question extracted from the past paper for Cambridge A-level exams. Okay, so this one says, using the following data and any relevant data from the data booklet to calculate the standard enthalpy change of formation. So standard enthalpy change of formation. Then they are saying include a sign in your answer. Show all your working. So they've given us these values that are here. And then we are trying to calculate for this one. So again, as you can imagine, we have sodium on one end here, and then we have N3 on the other end here. That's how they came up with NaN3. So this is what we have. Now, you know that this will eventually be atomized from the solid to a gas, but it will eventually end up as Na+, meaning it is only going to need what? One of these guys here. So meaning in your additions there, this one here, you should be able to put 1 over 2, which is the same as 3 over 2, so that you can get rid of this one. This is where this guy here, you've been given this one as a guide in your calculation. So this is where this one is coming through. Now, let's look at this one. Let's look at this one. So here we are saying the only thing that is missing here is the ionization energy for sodium, which you are supposed to get from the data booklet. And take note that all these things are given in kilojoules per mole. So in the data booklet, because here they've given us lattice energy, here they've given us enthalpy change of atomization, then they've given us enthalpy, standard enthalpy change. So this one is a general. So depending on the nature of what is happening here, we need to figure out which part this is representing. So let me just create some space so that we can figure out together which part this is representing. So now, the sodium will first be atomized, and the atomization is represented here. Then after atomization, we're going to have ionization energy, which is not in this table provided. So we need to go to the data booklet. Okay, we need to go to the data booklet. That's where this value was gotten. Okay, we are done with this one. Then on the part for the N here, the N2 or the N3, here you know that it first has to go through dissociation, and then after dissociation, it goes through electron affinity. So now, have they given us the electron affinity here? Before we can say no, let's look at the title here. The title says standard enthalpy change. Now, what they've written here, look at, they've written this one, which shows dissociation, but they've added an electron. So addition of an electron to a gaseous atom here is defining electron affinity. So this value that has been given here is an inclusive value for dissociation energy plus the electron affinity. So when you write the general equation here, enthalpy change of formation will be given by atomization energy plus ionization energy plus dissociation energy plus electron affinity plus lattice energy at the end here. So when you check here, you can't see dissociation energy and you can't see lattice energy. That is because these two have been combined into the 142 kilojoules per mole based on the way they've written the equation here. So that is how you are going to plug in this value. So the enthalpy change of atomization is plus 107 as given there. Then here we have the ionization energy for sodium, which is 494, which is here. Then we have the 142, which is representing both dissociation energy and electron affinity. Then we also have the lattice energy here. They've said lattice energy for this whole thing is negative, that one. So when you plug in the values, you eventually come up with what? Plus 11 kilojoules per mole. So that is how you can calculate the lattice energy. You should bear in mind the Born-Haber cycle. The steps of the Born-Haber cycle, they are the ones that are going to guide you. Which one do you have, which one you don't have, and so on and so forth. Let's do a sample exam question from October-November series 2020 question paper 4.2. So this is question paper 4.2. So this one says the energy cycle shown can be used along with suitable data to calculate the enthalpy change of hydration of calcium cation. Each arrow indicates a transformation. So we have W, X, Y, and Z. Each transformation consists of one or more steps. So they've given us this one here. Let's keep on. So the first thing they're saying, the following data and data from the book, the data booklet should be used. So if this data that has been given here is insufficient, they are saying we can also use the data booklet. Thankfully, in the new way of them bringing exams, all the data that you need is actually attached at the back of your question paper. So we don't need to worry about that. Now we just need to figure out here. We need to figure out. So when you look at this diagram here, you need to understand. They are saying calculate the value of the enthalpy change corresponding to transformation W. So you look at W. W is from here. From this level. W is from this level going to that level here. So now you ask yourself, remember, the first thing you ask yourself is, how did this calcium solid move to Ca2 plus and gas? Meaning there are two things that happened here. This calcium, first of all, was atomized. It moved from solid to gas. So there is enthalpy change of atomization. So this W, if you look at it, there is atomization represented, okay? There is atomization, then there is 2 plus. 2 plus means there are two ionization energies. So there is first ionization energy, okay? Then plus the second ionization energy. So there are two. There is first ionization energy, which was supposed to give us Ca plus, and then the second ionization energy, which is giving us Ca2 plus. So we've analyzed that one. Then let's also look at this scenario here. Okay, here we have Cl2 gas, and then here we have 2Cl negative gas. So what has happened here is it has been dissociated. So we can see dissociation here. Okay, so there is plus dissociation. So this Cl2 has dissociated into two individual Cl2, but it also has a negative here, which means the electron affinity. Okay, it also has a negative here, which means what? Electron affinity. That's what it means here. So meaning if we are to find W, then we should find the value for the atomization of calcium, then we should find the value for the first ionization of calcium plus the first ionization of the first ionization plus the second ionization, and then dissociation of chlorine and the electron affinity. That's what this transformation W represents. Once you figure that out, then you'll be good to solve W. So let's look at what was missing was the first and second electron affinity of calcium. That's what is missing here. It's not there. If you check, we have atomization, okay? We have all these other ones. We have electron affinity, but we don't have first and second ionization. So this can be gotten from the data booklet. So the equation that we made in the previous, from the previous slide, let's look at how we can now substitute. So we have the atomization, the first ionization energy, second ionization energy. Then on the electron affinity, because there's a 2 in front, there's a 2 in front on the diagram. That's why we have to multiply by 2. So you substitute, you are going to have these values, which you are going to get, and then you have your final answer as this one here. Using your answer to A1 and other data to calculate the value of the enthalpy change corresponding to transformation Z. Now, the first thing that you need to find out is, what does transformation Z represent? So transformation Z represents lattice energy. Transformation Z represents lattice energy. So meaning you are supposed to write the overall equation. The one I said you should memorize and just substitute. So the enthalpy change of formation is equals to the enthalpy change of atomization plus enthalpy change of ionization plus dissociation energy plus electron affinity. All those, and then plus lattice energy, and then you substitute into that equation. So we can just write it like this here. So meaning here we have the x. So here we have x plus y, because there are two things that are involved in here. Look at the arrows. This arrow is facing down. This arrow is also facing down. So meaning in the actual sense, let's examine what w, we saw what w stands for. Then x actually is supposed to stand for the enthalpy change of formation. Why? Because we've added calcium in its elemental state plus chlorine in its elemental state, then it gave us calcium chloride. According to this arrow, it's coming down. Then from this solid, we turned it into aqueous. Aqueous is a solution. So this is an enthalpy change of what? Solution. Okay? Enthalpy change of solution. That's what it means here. Okay, so once we know those things, in order to find the lattice energy, which is Z here, there are two things. You can make an equation, because the arrow W has got an up arrow, and then Z also, they are facing in the same direction. It's like the arrow is starting like this, it is going in the same direction. So those, you can sum them up as W plus Z. Then also the arrow for x and y, they are also heading in the opposite direction. So because they are heading in the same direction, there will be x plus y. So x plus y should be able to give us w plus z. So once you substitute the appropriate equation, then make z the subject of the formula, you are going to get your answer as this one here. So the lattice energy in this case will be negative 2355 kilojoules per mole. Now, you just need to understand here, what you are finding is lattice energy. Then lattice energy, you are supposed to add all this starting from x, w, and whatever will be given here. But because it was a little bit straightforward, we had to use what we have to get what we want. Just on the concept of the arrows. X and y, they are facing in the same direction, so you should add them together. And then w and z, they are facing in the same direction, so they should also be added together. So you come up with this initial equation, and since you are finding the value for z, you can just substitute the value for x, okay, so the value for x here, x, like I said, is the enthalpy change of formation. So when you check for which one is the enthalpy change of formation, which was this guy here, the negative, this one, that's the one we wrote here. And then the y here is the enthalpy change of what? Solution, which is the one which is here, and then we substituted in here. And then this value for the value for w here is the one that we found from the previous question, and we just substituted it after making z the subject of the formula, and that is how you deal with this question. Using your answer to A2 to calculate the enthalpy change of hydration Ca2. Now remember that in this question here, they've given us this one here, enthalpy change of hydration of Cl2, of Cl. So now the enthalpy change of hydration, so here the enthalpy change of hydration of, so the whole thing here, we are using the one we are just from finding. So the one we are just from finding is this value here, because when you check this arrow, it's finally ending here. So the lattice energy is, in this case, is actually also the same as the enthalpy change of hydration of CaCl2. Now the enthalpy change of hydration of CaCl2 is a total sum of enthalpy change of hydration of this guy plus this guy here, Cl negative. And then this one will give us the CaCl2 like this. That is what. Now, if in the equation, in this data here, they've given us the hydration for Cl. Okay, they've given us for Cl. And then we have also found for this one. Meaning the only thing that is missing is this. So we can make an equation and just substitute or make Ca2 plus subject to the formula, and then it should be able to give us the answer. So let's see how that can be done. So understanding and data collection is something that is very important with regards to solving these things. So here we are saying enthalpy change of hydration of calcium plus enthalpy change of hydration of chlorine will give us the lattice energy or the enthalpy. So I said this lattice energy is the same as the enthalpy change of hydration of the whole thing. So that's what you do there. So this one here, if you want, you can make it x. Then there's a 2 in front. Remember when we made the equation there was a 2. So because we said it's plus 2Cl negative, that's why we are multiplying this value here by 2. Very important stoichiometric coefficients, they are part and parcel of the equation. So that is going to be very important. So we substitute here, this one will be x, meaning when you multiply this guy here, it will just cross over the equal sign here. And then when you do the proper computation, this is the answer that you're going to come up with. So here they are saying write an expression in terms of W, X, Y, and OZ to show how the enthalpy changes of two of the transformation can be used to calculate lattice energy of this one. Now we know that here the first one we are saying it's Z minus Y. So this Z minus Y. Why are we saying minus Y? Because we know that when you are finding the enthalpy change of formation, you add enthalpy change of formation, you add this plus that, and then plus something that is supposed to be here. So you can easily subtract the y here. If you remove the y, everything that remains should be able to give you what? The lattice energy, which is this one. Okay? And also x minus w. So x minus w, when you subtract, because this x is facing in the opposite direction, so when you remove that x from whatever w represents, you'll be able to find the lattice energy. Then state whether the lattice energy of CaCl2 is more or less exothermic than lattice energy of MgF2. Explain your answer. So here, your answer will lie in the fact that you need to check the size of the ions. Which one has got bigger ions? So the one with bigger ions is the one that is going to give you larger lattice energy. So in this case, we are saying it is going to give us less, it will be less exothermic because both ions in CaCl2 are larger. Okay, less exothermic because both ions in CaCl2 are larger. Thank you so much.